Thank you, Professor Zhu, for the introduction. And I would also like to thank Professor Ronel Wickerman-Shinke and also for making almost all my widget in Australia. And for the widget over here, I would thank Professor Xiang and also Professor Ricky Chen for making an arrangement for my widget here. It's my great pleasure to have this opportunity to talk about some of our research work on fabricated transfer membrane. Let me see. Let me try to find my point. I saw I found it over there. Okay, thank you. Okay, this for fabricated transfer membrane for CO2 capture from flue gases. My co-authors are Dr. Yang Han and Dr. Yitong Yang. Okay, here's the outline of my talk. I would introduce on the carbon capture from flue gases, fabricated transfer membrane. Then I will jump into the membrane scale-up, membrane module, and process validation and the field test. And then I give a brief summary. As you know that flue gas, the low pressure, one atmosphere, same pressure as what we have in the room here. Low CO2 concentrations, depending on the type of flue gas. For the natural gas combined cycle, NGCC for short, not only had 4.1% CO2 concentration, but if you use exhaust gas recirculation, EGR for short, that can increase to about 8% concentration. For the natural gas boiler flue gas, about 8% CO2 concentration. For coal, you can get up to 13% CO2 for the electricity generation. And for cement, can get up to 22.4%, getting higher and higher. For the steel industry, some flue gas there can get up to more than 30%. Okay, the higher the concentration, will be easier for the capture and also with much lower capture cost. So for all those cases, the driving force is low. However, the U.S. Department of Energy's capture target is get up to at least 90%, and more recently we get up to 95% degree of capture, and then we see the purity of at least 95% and higher. So I mentioned about the exhaust gas recirculation. Here you take a natural gas, gas turbine, and that can turn the gas turbine, and you can generate electricity. And the flue gas coming out here can have a heat recovery and steam regeneration, and you can turn the gas turbine. Can also generate electricity. That's what we call a combined cycle. And if you flue gas come out here, you use the post-combustion CO2 capture. That's what I'll talk about today. And then if you recirculate these flue gas, combine with air to burn the natural gas, and this so-called exhaust gas recirculation, then the flue gas come out here can get up to about 8%. For our membrane, that we use nanoporous fabric, that's polyethylene thiazide, nanoporous fabric, just like the one used in the reverse osmosis membrane. And then we put a nanoporous polyether subform with thickness of 30 microns, pore size average is about 35 nanometer. That allows us to make the core is in there, membrane 170 nanometer, nanometer thick, and that's for separation of CO2, from nitrogen. And in this selective membrane, we incorporate so-called fixed site carrier, which is the polyamines. The amino group is anchored to the polymer chain, so the CO2 react with amino group has to hop from one amino site to the next in order go to the permeate site, where it's the reverse reaction release the CO2 to the permeate site. We also incorporated so-called mobile carrier. That's a small molecule containing amino group, and that can also react with CO2, and the reaction product is also mobile. They can diffuse across the membrane. So the CO2 can also go through the membrane through the so-called physical solution diffusion mechanism. However, that's very, very slow, and just like nitrogen cannot react with the amino group, so they can only go through the membrane through the solution diffusion mechanism. So that way, with the amino group incorporated inside the membrane, we can foresee the CO2 transport, so we can obtain a high CO2 permeance and also high CO2 nitrogen selectivity. Here we plot the CO2 nitrogen selectivity, so-called Robertson plot, versus the CO2 permeability, and many polymeric membranes such as rubbery and also glossy material. So rubbery would be a polyethylene type glossy membrane, could be a polyimide membrane. All those are below the Robertson upper bound. However, the free-shear transport can go higher than this upper bound. So we use the fixed site carrier, which is the polymonoamine, and here we're showing 3 different types of mobile carrier. This is piperazine, and then glycinate. So this is amino acid salt. The next one is piperazine azo, amine glycinate. Okay. Then the third one is piperazine azo amine sarcosinate, which is one methyl group to the nitrogen side to increase the degree of stick hindrance to the nitrogen side. Now, all those, because you are seeing the performance in order of 1, 2, 3, go up beta and beta. And for the piperazine azo amine sarcosinate, that's our 4th generation of membrane. And so that I'll show you more on the performance and also the membrane that we have fabricated. So this slide illustrates the carrier saturation phenomenon. So you're seeing the CO2 permeance that reduce at the 3 temperatures. Okay, as the CO2 partial ratio increases. And what's happening over here is that we can only incorporate so much amount of amino group inside the membrane. And if someone tried to come in, couldn't open the door. So when you have a high CO2 partial ratio, in the gas phase, flue gas, and that's going to react more of amino group, inside the membrane. So therefore, the free amino group inside the membrane will reduce. And as that, then the CO2 permeate is also going to be reduced. Okay. The reason for 57 degrees Celsius, that's the typical average flue gas temperature in the coal-fired power plant. And then we all know increase temperature typically will increase 10 degrees each. So that's why I get up to those temperature over here. So we have developed a simple model based on the first principle over here, then showing that the permeance, there's a permeability divided by the membrane thickness, that's permeance. And with the subscript 0 means there's no precipitation, okay? And that will be all this based on solution diffusion mechanism on here. To account for the precipitation, there's a EDA over here. And then PA star, that's the onset ratio where you start seeing the significant effect of a partial ratio on the CO2 permeance. Okay, and then this is the height on the free side ratio of CO2. So this simple equation were able to model this preceded transport mechanism, taking the carrier saturation phenomenon into account. Here Now we are plotting the CO2 partial ratio, since this is in the flue gas versus the flow of over the membrane, of flue gas over membrane. So here is the inlet of flue gas, and here is the outlet of the retentive, going up. And if we only remove 30% of CO2, then this line is almost pretty much linear. However, when you remove more, you can significantly reduce the CO2 partial ratio in the gas phase as CO2 permeates through the membrane to the permeate side. And so if we only remove 30%, the CO2 permeates, that's in the red color, it's only about 1,000, over 1,500 GPU. Okay, and when you remove 90%, the CO2 concentration in the gas phase is much reduced, and then can enhance the CO2 partial ratio to 2,000 GPU. This gives you the gas permeation unit. That's the typical unit that we use in the gas permeation. So if we do not take the carrier saturation phenomenon into account, then the membrane area would be much higher. And after without taking into account, because as we say, the CO2 permeance increase significantly as the CO2 partial ratio reduces. So we can get these membrane area reduced significantly. So for a given fractionation factor and also the onset ratio. We look at the two pathways for the CO2 amino group reaction. So for the carbamate pathway, because this carbamate ion is stable, so we need another more of a carrier in order to neutralize, to absorb the proton from the carbamate acid from the carbamate ion. So that become positive. So here we need two more amino group in order to capture one more of the CO2. However, if the amino group is still hindered, then the carbamate ion is not stable, and that can react with water to form a bicarbonate as a sink. For this case, you only need one more amino group to capture one more of the CO2. And we work with Professor Li Changlin. Now he's at the National Taiwan University, and he did density functional solidity calculation, showing that if for this amino compound, that's our Gen 1 membrane, and that gives a much more stable product. Okay, so means this this amino compound prefer follow the carbamate pathway. Versus the new carrier that we're looking at, essentially we're using the density functional solidity calculation to screen over the different type of amino group that we want to incorporate inside membrane. So more recently we found out that with the guanidine group, and then this is much more sterically hindered, and then the reaction product is much more stable. So they get much more stable means that the energy level is much lower. So that way, this new carrier can favor the bicarbonate formation, and then give a higher CO2 purity. But CO2 absorption capacity, so can have a higher CO2 permeance. And we did synthesize this into the polymer too. In the essential we synthesize the polyethylene guanidine, and then we're showing the CO2, the selectivity and also permeance. So for a conventional polyamine such as polyethylene, polyvinyl amine mentioned earlier, and that is below the represent the upper bound. But for the new carrier that we have synthesized polyethylene guanidine, we're able to go above this upper bound. And then when we add the mobile carrier, essentially we can add something like our Gen 1 mobile carrier in here, and then we can go up to a much better performance. We can get up to 4,000 200 GPU permeance and selectivity of greater than 160. Here a summary of our three type of membrane that we have synthesized. The Gen 1 membrane, that's one I mentioned, based on poly. The mobile carrier is purities, succinate. And then then the Gen 3 membrane, that's the one I just mentioned, based on the polyethylene guanidine. Then we can get up to 4,200 GPU, and with selectivity of greater than 160 at 77 degrees Celsius. 77 degrees Celsius. In between, we also developed one of the intermediate membrane that we call it Gen 2 membrane. So we are pushing the membrane performance to higher and higher in order to reduce the CO2 capture cost. So after we have identified membrane in the laboratory, we're able to scale up, using the pilot machine we had, in the roll-to-roll, fabrication. We are on one roll over here. Essentially, these would be the poly insufficient nanoporous substrate on the nonwoven fabric, and going over the coating, and then going into the dryer, and then we can pick up the membrane over here. So after we have scaled up the membrane, then we can roll into spinal one of the membrane element, and then we'll place the element inside a housing to make the membrane module. And here showing we have fabricated 8-inch diameter, which is the commercial diameter, just like a reverse osmosis membrane, and 22 inches in length. That contains 41 membrane leaves, and the total membrane area is 35 square meter. Essentially, that's all the commercial size. And you're seeing the module, every the cross, the side view, and then partially exposed view of the module. Okay, so we took this module and we pushed inside the environmental control chamber, essentially oven, to maintain 77 degrees Celsius. And we took that to University of Kentucky, the Center for Applied Energy Research. That's their coal-fired boiler, and then produce the flue gas, and we connect to our unit for the testing. You can see over here, initially, they could not control the CO2 concentration, at the, typically it should be about average is 9.4% CO2, okay? And that's why you see a little bit of fluctuation. But they don't able to control the 9.4% CO2 concentration, obtain a very stable CO2 permeate. So this is 4,200 GPU, and selectivity also higher than 160, and that's contain some SACs and also NACs in there. We have developed a two-stage process for CO2 capture, 90% CO2 capture from the coal-fired flue gas. And so the flue gas coming out, goes to the field, we use a blow to get up to 3.5 atmosphere. And CO2 permeate membrane preferentially, and we're able to get up to 37% on the stage 1, and then come to stage 2, we're able to get up higher than 95% CO2 purity. So the retention come out, we took part of that, about 15%, and used that as the internal fluid, on the permeate side, and then come out from the stage 2 will be recycled back over here. The pattern come out in 2022. Here is based on the two-stage process. We have construct the integrated skid. So we have a stage 1, using this 35 square meter membrane module, and stage 2, since volume is much reduced, we only need to use 12 square meter membrane module for this two-stage skid. And we took this skid to we test up with a similar comb, and also natural gas combined cycle flue gas. Under the steady state testing, we are able to obtain at least 90% of CO2 capture, and then the CO2 purity on the permeate side also higher than 95%. Based on the first principle in chemical engineering, including the momentum, heat, and mass transfer, so we are able to predict the CO2 purity, that agree with our experiment data quite nicely, and so the capture degree can also predict quite nicely. And when we did the parametric testing, we were able to on the 90% capture in blue color, then 95% capture, and then 99% CO2 capture. Then after that, we did for the simulate the natural gas combined cycle, and again we can get up to 90% degree of capture and purity of at least 95% of the CO2 purity. Then we took that skid to National Carbon Capture Center in Wilsonville, Alabama, and we test the actual natural gas boiler flue gas that contains 8.6% of CO2. And you can see that we're doing the testing. We did the parametric testing first. We start with 99% of CO2 capture, and then 95% capture, then at least 90% capture, and then the CO2 purity is all higher than 95%. And then we encounter the boiler, shut down. There's some mechanical problem. We did not have a flue gas for about 500 some hours. And then as long as the flue gas returned, then the membrane performance restored. Now again, greater than 90% CO2 capture, and the purity is greater than 95%. Then after that, the National Carbon Capture Center dilute the natural gas boiler flue gas from 8.6% CO2 concentration down to 4.3% CO2 concentration using air. And we did the parametric testing for 90% capture, 95% capture, and 99% capture. All the capture CO2 is all higher than the 95% purity. So one of that 35 square meter membrane module I mentioned that we test all kind of simulated flue gas, and here is 100-hour testing at the University of Kentucky at the Center for Applied Energy Research. Okay, there, and then after that we also did the simulated core flue gas, then all different kind of flue gas, and then we the actual natural gas testing. That's at the National Carbon Capture Center, and we kept running, and now we are still running in our lab. This slide here showing over about 6,000 hours, and as long as we return to the original condition, and then the performance restored. And we keep going as I'm talking here. This data has been generated, and data showing here 16 months. Actually, right now it's more like 17 to 18 months now. So all showing a very stable result. Okay, and we are putting 3 of element together with the interconnector in the same membrane module housing. Now we can get up to 105 square meter membrane area. So we're going to capture 20 tons a day of CO2. And this will be demonstrated at the Wyoming Integrated Test Center near Gillette, Wyoming, in next spring 2025 next year. You can see the size of module with one of our research over there. So in summary, that we have developed a membrane with very good performance with a CO2 permeance of 4,200 GPU, selectivity of at least 160. We have scaled the membrane module, and then we have fabricated commercial size with 8-inch diameter. And importantly, membrane has shown consistent result. From the flashy sample as small as the 1 inch the diameter to the spider one, the membrane module, and also to the skin. From assuming the flue gauge to the actual flue gauge, all consistent result. So we have demonstrated a good membrane module and process stability, for more than 1 year. And at the National Carbon Capture Center, we're showing 90 to 99% of CO2 capture with a purity of at least 95%. CO2 purity from the natural gas, boiler flue gas, and also the chimney natural gas combined cycle flue gas. And I mentioned we have at least more than 1.25 years of membrane module stability. So thanks to many people, and the funding comes from Department of Energy and also Ohio Department of Development. I will leave this slide here. Hopefully, our work will keep the great show for our future generation. Thank you very much for your attention. I'll be happy to answer any question I may have. I think about 30 minutes.
Thank you very much, Professor Ho. I think it was a very nice talk with a mind-blowing plot with the x-axis exceeding up to like 6,000 hours. I think it was hilarious. Any question from the audience?
Thank you for the very wonderful presentation from fundamental membrane fabrication to scale up. So my question is about, we are the research and academic, and then we are PhD, more fundamental study, and then scaling up, like you have experience for the flat sheet, like fabricated.
Okay, not only internet, we're using taxpayer money. We got to get something in return.
I see.
To our society.
Like, okay, we have a lot of membrane fabricate from the lab. So based on your experience, scale up scale up the spiral round module. So it's better to have a know-how and how we can set up this kind of scale up membrane, or do you have any some tips because we want to think about what's the best way to scale up for the membrane with this kind of spiral round 8-inch or 4-inch module. So based on your experience, it's better to give to somebody who already experienced, or if you have you want to make this kind of module, so how long it takes and what's the difficulty we would face?
Okay, the reason we have chosen spiral wound module.
Yes.
Okay, there are many factors that we have taken into account. As you mentioned, we are academic institution. Right. Okay, so and we will not manufacture the membrane, for the commercialization because that's beyond our charter. Okay, but we do need to create a commercial prototype So that way that the membrane company
Yeah.
can take what we have developed, and then hopefully they can get into the commercialization. And almost all the desalination membrane is based on spinal winded membrane module. And this is exactly that's why we chosen the spinal winded module. We have fabric, pre and frame module before, and certainly the color fiber module cannot be fabricated too. But again, the reverse osmosis desalination membrane is most well established membrane industry. Okay, well, probably know now. They all use spinal winded module.
Yeah.
So we're counting on them to take our commercial prototype and to commercialize. Okay, so if you make a pre and frame module, I do not want to mention some of our research organizations or companies. Okay, some of them are doing that. They're going to be very limited. Membrane company would be able to do that. But for our case, they just can take it. In fact, we are working with desalination membrane company right now. Okay, to scale to commercial our membrane. Hopefully, commercially. Okay, so not all the membrane material certainly. With our good imagination, we maybe will come up with a lot of very interesting, very good membrane material. But not necessarily all the membrane material will be able to be scaled.
Yeah.
Okay, not necessarily. Okay, so for me, I come from industry. I advise my students, do not waste your time doing something that's not useful. Think hard, do something that's useful.
Yeah.
Whatever we do, we hope that will turn into a technology that can benefit, our society. That's exactly what we're doing. Did I answer your question?
Yes. Yes.
All right? Okay.
Interesting topic. Just my question is, what's the lifespan of that module? Because you said it's been running for 18 months and it's still going. So, is that fine, definite? Or
Okay.
there's
Actually,
more?
I got it out.
Yeah. What is it?
Okay. I'm showing you 16 months data right here.
Yeah.
Perfectly stable.
Right.
We did not see any degradation. So we believe
Yeah.
this membrane will last at least 5 years.
85 years.
5 years.
5 years.
At
5 years.
least 5 years.
At least 5 years.
Not 85 years.
Yeah.
85 years.
Yeah. At least 5 years. Right.
Okay.
Okay.
At least
Yeah,
5 years. So I would think based on the data we have, we can project or associate. We can estimate could be longer than 5 years.
Right.
Okay. But average membrane life right now people are using is 5 years, based on the interfacial polymerized desalination membrane. It's about 5 years. So we have a very good chance, to do that.
Interesting. Thank you.
Okay, welcome.
Thank you very much for an interesting talk. It's really inspiring. As far as I know, in slated transport membrane mechanism, usually the leaching out of the carrier is something that the many researchers face during the experiments. I wanted to know what was your trick that no leaching out was observed after almost 1.5 years.
Okay. Leaching out, I will assume you are referring to the liquid phase.
Yeah.
Fortunately, our membrane is designed for gas phase. Okay? So there's no leaching unless you intentionally flood the membrane module in water, which we do not intend to do. Okay? We only treat the gas phase. So, okay. You may say, how about if you could not control your temperature, then there's water condensation, which encountered sometimes during the night. And as long as we get the temperature under control, performance restored. And the temperature control, we only need to do it, plus or minus, 1 degree Celsius. That's more than what the membrane should experience, or the membrane should be able to take that. Plasma 10 degree Celsius temperature control is a piece of cake. Okay, actually, the oven I show you, we can get to plasma 0.1 degree Celsius. Okay, but plasma 1 degree Celsius is good enough. The reason I'm showing this slide over here, we intentionally use the amino acid salt. Okay, every one of them is amino acid salt. Okay, means there's no volatility of those compounds to get into the vapor phase. Okay, and if there's any volatility, no way we can show. I can show you data for 16 months. Okay, so the carrier is not going to go anywhere, and unless you're going to intentionally soak in the water, which we do not. We advise any user not to do it. Okay.
But in industry, usually, if you want to go to CO2 capture, for example, in power generations.
I'm sorry, I missed that.
Okay, I mean in real industrial application, for example, in power stations, power generation plants, CO2 stream comes with lots of humidity. I mean water.
Okay, all the gas phases, gases is all saturated with water vapor. Okay, can be and most is saturated with water vapor. Thank God our room is not saturated. The air is not saturated with water vapor. Okay, I think right now maybe about 60% relative humidity. Okay, and we are taking all the flue gas, or even the similar flue gas that we do, is all those gases are saturated with water vapor. Okay, and that's all the data I show you. All means all saturated with water vapor. So there's no issue with saturated, water vapor in those flue gas. All right, we did not see any degradation or any of those issues. So it's fine. We expect all the flue gases should be saturated with water vapor at a given temperature, and that's no problem at all. Okay. Can you think of some cases that the membrane may be flooded with water? No, I don't think so.
Yeah. Yeah, thank you.
Andrea?
Thank you, very nice presentation. Just on this slide here, I have one question. These mobile carriers and fixed site carriers, is this something you have developed in your lab, or is it something commercially available?
Okay, this is very cool. Everything we created.
Okay. Yeah.
But the compound, who all I'm showing over here, all the ingredients are commercially available. Okay. For example, you can process the polyvinyl, but you can turn the degree of hydrolysis, which you can modify. Okay. Here, certainly we do modify. We control the degree of hydrolysis. Yeah. Okay. But this polymer is commercially available. We also follow the literature, and then we also make some modification. We are able to make this polymer, which is commercially available only about 2 million molecular weight.
Okay.
We can get up to 20-some million. Okay. The higher the molecular weight can enhance the mechanical strength of membrane. That's the reason we did that modification. Okay. Then for example, you can process purities, which is commercially available. Okay. You can also process glycerin. Actually, that's some molecule in our body too. Okay, glycerin. Okay. So, and then we should react the purities with glycerin to make this question there. So the only thing my student need to do is to process, preparation, process, glycine, and then react them to make an amino acid salt.
Yep.
Okay.
Okay.
So but there are some newer polymers such as polyethylene guanidine. Okay, I mentioned. Okay. That polymer has been synthesized before, but at a very low molecule for different application, bacterial sites type of application. But for our application, that low molecular way will not work. So again, we can learn how to polymerize that new polymer to obtain the molecular weight of. Right now we can get more than 2 million molecular weight. Okay, which is not easy.
Yeah.
Okay, but we did it.
Thank you.
Winston, can I ask you a question?
Sure.
So for these very long run times of several years, is membrane fouling not an issue? Is the feed stream relatively clean, or
Gas separation is very much different
yeah?
from a liquid separation. Okay, it's not that much of a fouling for gas separation, but the particulate fouling can happen. That's the reason we have a filtration. Okay, I show you that one. We have filtration. Typically, we use about 5 micron filter. That most of applications good enough. But if some, for example, in University of Kentucky, that the boiler flue gas that with Ohio coal, by the way, it was very dirty. Okay, so after that, we got the also follow up with 1 micron filtration. So if we did the filtration, remove all those particulates. So anything is flowing with the gas phase, they all going over. And this because our membrane is extremely hydrophilic. So even with some hydrocarbon, for example, methane or even up to butane, okay, those in the vapor phase, in the gas phase, they do not like our membrane, so they do not stick. They all going out. Even a lot of heavy metal, particularly the flue gas coming out from the core file flue gas, including arsenic, selenium, mercury, okay, and cadmium. They did not deposit on our membrane surface either. We look very hard try to see whether any of those heavy metal deposits. Main concern is for future disposal of our used membrane module. Okay, we found nothing. Okay, so they did not stick to our membrane.
Any other question? Can I ask one question? Yeah.
Okay, very good.
Yeah.
You can have more than one. You are the one controlling the time.
I think we have.
But certainly I do not want to take away your Ramian cup.
Okay, so those mobile carriers, adding those carriers to the membrane will facilitate the dissolution of the CO2, but also I think it will be acting as a plasticizer, so it will make the polymer chain more mobile. The segment of motion will be enhanced, in my opinion. And
Sure.
And then you showed that I think it was in the previous slide that showing the 3 different mechanisms of the CO2 transport. And does the addition of the carrier not only facilitate this dissolution, but also does it enhance the motion of the polymer chain so that it increases the transport of the CO2?
Good point. Okay, as mentioned, we do need a high molecular polymer in order to maintain the membrane mechanical strength. Okay, but that's the reason we got to put in the fixed site carrier. Essentially, that's to maintain the membrane matrix mechanical strength. Okay, certainly the amino group also offer the facilitated transport of CO2, but this is much slower because not this involve the forward reaction of CO2 with the amino group in order to form either carbonic ion or form bicarbonate ion, right? And in order to hop from one side to the next side, the reverse reaction need to take place to release the CO2 and then get into the next side. So there's a forward reaction and a reverse reaction got to take place, okay? Sequentially, okay, for each CO2 molecule to go through these fixed site, carrier. So then the reason for forward reaction and reverse reaction take place because their CO2 partial ratio different. The higher in the free phase and low in the permeate side. Okay, that is driving for the forward and reverse reaction. So it means for each fixed site carrier CO2 got to go through the forward reaction and reverse reaction. And then you have many of, I'm sure they can go through many of them, right? So they're repeating all those, forward and reverse reaction many times in order to go across the membrane. But for the mobile carrier, you only react only once, and then they diffuse. Okay, so that's the real, become obvious. The mobile carrier is run doing most of felicitation.
Like a shuttling of the
That's right. Yeah. So that's the reason we got to incorporate the mobile carrier in order to increase the CO2 permeate. But both are needed, otherwise we cannot make it. Membrane to work.
Thank you very much. Okay, if there's no other question, let's thank again Professor Ho.
Yes,